All right, we're now going to cover what I would argue is the coolest topic of the semester, which is optimization. So, optimization is going to allow us to take these things we know about finding the minimums and maximums of functions and actually apply it to something that we could try to, minimize or maximize. So, these methods we've had for finding extreme values have a lot of practical applications. Say a business person wants to minimize costs or maximize profits. We've got someone who's trying to travel but minimize the amount of transportation time or maybe the cost of the transportation that they have. Some sort of bird wants to try to maximize the distance it can travel without stopping. In this section, we're going to basically look at everything we've done up until this point about calculating absolute mins and maxes and use them to solve optimization problems. The goal of an optimization problem is to make a decision that is the best possible for some quantity. And when we say best possible, we really are saying either we want to minimize or maximize that quantity. So the function that we're trying to minimize or maximize is called the objective function. Later in the notes I might use OF to kind of help denote what our objective function is and kind of key in on what it is. So the function that we're trying to minimize or maximize is called the objective function, and oftentimes, but not always, our goal is going to be restricted by something known as a constraint, or maybe we'll have multiple constraints. So say we were that business person who wanted to maximize their profits. However, you're going to be constrained by the amount of demand there is. Maybe it's that demand has to do with the season it is, the cost of making whatever the product is, or whatever the item is that they're selling, the supply available, the rate of production. You can also think of this then as a bit of a time constraint. And say we're that traveler and we want to minimize our transportation time or cost. However, we're going to be constrained by things like traffic, stoplights, weather, construction, trains, accidents, so these are things we'd have to keep in mind as we were trying to solve the problem. It'd be nice to just be able to go, but every once in a while we have to consider some of these constraint equations. So say we want to go ahead and start solving an optimization problem. Here are our steps for solving those. First thing we're going to do is we're going to try to get some sort of picture and figure out what our variables are going to be, right? So unlike most problems we've seen, we're not being given a function and told, okay, optimize this. We're going to have to actually figure out what the function is that we want to go ahead and optimize. From here, we need to identify that goal of the problem, and that's how we create our objective function. Figure out, okay, what do we want to minimize or maximize, and then we have to figure out how we're going to get there. Now, from here, we also have to consider if we can use our constraints in any way to try to get us down to one variable. So not every problem is going to have just one moving part, right? Every once in a while we're going to see problems that have more than one variable. What we'd like to do is we'd like to see if we can use our constraints to help us narrow down and rearrange things so that we only have to deal with one variable. Now from here, we'll go ahead and find the domain of our objective function, and then we'll find our derivative in critical points. We don't stop here. This is not a critical point problem. We then have to verify whether the critical points give us a global max or global min, and we then have to find the global min and max. The method you might use to do this will vary depending on your domain. Remember that our ways of doing this will usually involve the first or second derivative test. And if we have a closed domain, a B, where we are considering the endpoints, make sure to also check the endpoints. So there may be values that we could see at either end, basically at one extreme or the other, as opposed to somewhere in the middle that may end up doing our optimization. So this set of notes is going to be all about examples. So we're going to see 4 different examples of how we would go ahead and go through all of these steps to get a picture, figure out what our variables are, determine what our objective function is, see if we have any constraints, and try to solve the problem. All right, so let's begin. Say we've got a farmer with 2,400 feet of fencing, and he wants to use that to fence off a rectangular area that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay, so there's a lot to unpack here. First, we should actually make sure we understand what it is that this all looks like. So we say we want a rectangular field. So we've got a rectangular field here. Use a few dash marks. And it's bordering a river. Here's our nice little river. It's a very pretty river. We know that he wants to go ahead and maximize the area here, but he only has 2,400 feet of fence. So we're going to need to figure out what sort of variables we'd like to use in order to help us with this. Now we know that if it's a rectangle, this side and this side of the equation should be the same, and this side should be the same as this side. However, we don't know what this side is, and we don't necessarily need to know that. So we're going to let x be the length of the field. I mean, technically, I guess from this perspective, it might look like width to us. If we turned it this way, it would look like the length of the field. But since we have the paper oriented this way, I'll call it the width for us. So this will be the width of the field, and this will be the length of the field. In the end, it's not going to matter too much if you call one length and the other width. It's a bit of a matter of perspective. So here we want to figure out what our goal is. So we're told that we want to have the largest area. So if we want to have the largest area, then we want to maximize the area of the field. So our objective function will be to find the area. And if you want the area of a rectangle, that's just the length times the width. So in this case, it'll just be x times y. All right, well now we have 2 different variables, and that might be a little bit much for us. So the next thing we should do is figure out if we have any constraints. Now we're told that we only have 2,400 feet of fencing, right? So the thing stopping us from just making this an infinitely large field is the fact that we only have so much fencing. So if we know how much fencing we have, then we have 2x plus y equals 2400. So this would be our constraint equation. It would be this whole thing right here. And that's because we know we only have 2400 feet of fencing. Notice we don't need 2y because this border is just going to be the river. So what are we going to do? Well, let's go ahead and solve for y in terms of x. So if we rewrite this, we get y equals 2400 minus 2x. And now we can plug this into the objective function. See that the area should equal x times 2400 minus 2x. So all we did was we replaced y with 2400 minus 2x. And this will give us 2400x minus 2x squared. And we want the area of this function then, represented by a of x. So now we're down to just one variable. Only one variable to deal with. For the context of what we've learned so far, that's kind of key. Right? Everything revolves around us at the moment having a function of one variable. So then we want to find the domain of our objective function that fits the context of the problem. So what we know is that x has to be greater than or equal to 0 and y has to be greater than or equal to 0. Well, how do we know that? Well, we can't have negative side lengths, right? So there will be no reason for us to have any sort of restriction there. Now we also know that we need to make sure that we don't use too much fence. So there will be an upper bound as well. So if we know that y equals 2400 minus 2x, we know y has to be greater than or equal to 0. Well, what this tells us then is that 2400 has to be greater than or equal to 2x, which means 1200 has to be greater than or equal to x. So what this means is that x has to be less than 1200. So we know that 0 is less than or equal to x, which is less than or equal to 1200. So the domain is going to be that x has to be in the interval of 0 to 1200. And it could be either of those. Although it most likely won't be. And the reason I say it most likely won't be is that it would then imply that the other side was 0, and that's probably going to give us an area of 0. So not super likely. Alright, so now we're going to go ahead and do what we wanted to do. We're going to find the derivative of this function. So remember, the objective function is 2400x minus 2x squared. So the derivative of this is just 2400 minus 4x. And what we want to do is we want to find those critical points. So a prime of x exists everywhere. So there's no domain issues to worry about. When we set a prime of x equal to 0, we're saying 2400 minus 4x equals 0. So 2400 equals 4x. So x will equal 600. So this might be, well, this is a critical point. And it might be a min or max. So what we'll do is we'll go ahead and check using our first derivative test. So if we know that a prime of x is 2400 minus 4x, we hopefully will be able to find out some things about a of x. So we know that 0 is one of our endpoints. We now have this 600 for x, and we know that we're stuck no higher than 1200. So we want to pick some point on these intervals that is going to be easy for us to work with. And I'm going to pick 100 and 1000. It doesn't have to be smack dab in the middle of these intervals. It just needs to be somewhere on the intervals. And all these zeros and ones are kind of easy to work with. So if we want a prime of 100, that'll be 2400 minus 4 times 100. So that'll be 2000, which is positive. So that means we're increasing at that point. So just a little bit of a note for us. A prime of 100 equals 2000, which is greater than 0, whereas a prime of 1000, if we go ahead and do that instead, we'll get negative 1600, which is less than 0. So that means that we are negative here, so we're decreasing. So because we're increasing and then decreasing around a critical point, we know that 600, x equals 600 has a local max. And so as we're going between 0 and 600, we're just going up. So 0, the function value at 0 will be lower than this. And at 1200 from here we go down, so the function value at 1200 will be lower than this as well. So then here at the end of the day, we weren't actually asked what the maximum area was. We were asked what the dimensions were that give us the maximum area, right? So just to review, what are the dimensions of the field that has the largest area? So we never actually care about the largest area, we just want to know how we get there. So one of the other problems you'll find when looking at optimization problems is what are you being asked to answer? So in this case, you're being asked to answer how you get the max. So the dimensions for max area are going to be x equals 600, and y we said would be equal to 2400 minus 2 times x, which we just said was 600, so it'll be 1200. So this will be 600 feet, and this will be 1200 feet. Now note when you're doing this problem that what you call which variable will cause things to be a little bit different. So what do I mean by that? Well, what I mean by that is that I called this x and this y. But if I had called this y and this x, then these answers down here should be flipped. So another thing you will have to kind of keep in mind as we're looking at optimization problems is the order we put our variables in and what we call our variables can matter and change things a little bit. So just a thing to think about as you're typing in. Alright, let's look at another example. Say we wanted to find the point on the parabola y squared equals 2x that is closest to the point 1, 4. Alright, so there's a lot to unpack here. We want y squared equals 2x. So whenever we have y squared equals 2x, that's going to be a parabola that faces to the right. So like if y equals x squared, that would be a parabola that faced up. So this is y equals x squared. So this would be y squared equals x. Here we have y squared equals 2x, so it'll be a little bit different for us. But we can still draw the general picture even if we don't necessarily label every point. Right, so we know that we're looking at a parabola that opens up to the right, and we want to get as close as we can to the point 1, 4. So maybe out here is the point 1, 4. And we'd like to make the distance between the parabola and here, whatever this x-y pair is, to be as small as possible. So, goal, minimize distance between the point 1, 4 and some xy that is on the parabola. So our formula for distance is the square root of x minus x1 squared plus y minus y1 squared. And that would be if we knew what one of the points was. So here we know the point 1, 4, so this means that our objective function is going to be the square root of x minus 1 squared plus y minus 4 squared. So this is the objective function for those playing at home. Alright, so now we know that this xy pair has to be on the parabola. So that actually will be our constraint. So the constraint here is that y squared equals 2x. And again, this is since xy is on the parabola. So if we're going to use this to rewrite anything, we should get x by itself. Alright, so this will pretty quickly become x equals y squared over 2. And then we can plug that in to the objective function. So now d will equal the square root of y squared over 2 minus 1 squared plus y minus 4 squared. All we're doing is we're taking that x from before and replacing it with y squared over 2. Now we can do a little bit of work to FOIL this out beforehand. So if we FOIL this out, we'll end up getting y to the 4th over 4 minus y squared plus 1. And if we FOIL this out, we'll get plus y squared minus 8y plus 16. And all of this is still under the square root. And so at the end of the day, d, which is now a function in terms of y, once we cancel out those y squareds, will be the square root of y to the 4th over 4 minus 8y plus 17. Alright, so now we want to know what it is that we're looking at for our domain. So at the end of the day, the domain here ends up being all real numbers because we're going to be able to have this part under the radical always be non-negative. So the domain is negative infinity to infinity since function under radical is always non-negative. So then with that being the case, we want to go ahead and do our optimization step. So that'll involve us trying to take the derivative of this function. So now we want d prime of y. And we're going to get something very complicated if we go ahead and try to use the chain rule. But that's what we can do. So say we want to use the chain rule on this. The outside function is the square root of y. The inside function is y to the 4th over 4 minus 8y plus 17. The derivative of the outside is going to be 1/2 y to the negative 1/2, and the derivative of the inside will be y cubed minus 8. So that means d prime of y will be 1/2 times y to the 4th over 4 minus 8y plus 17 to the negative 1/2 times y to the 3rd minus 8. Or we can rewrite that as y to the 3rd minus 8 over 2 times the square root of y to the 4th over 4 minus 8y plus 17. Now from here again, we want to be able to find these critical points. So those are places where the domain, the derivative does not exist, or where the derivative equals 0. So if we look at where d prime of y equals 0, we'll have y to the 3rd minus 8 over 2 times the square root of all this awfulness equals 0. And when we multiply all this awfulness over, we'll get y to the 3rd minus 8 equals 0. And so if we do that, we get that y to the 3rd equals 8, and then we have to take the 3rd root of both sides, and we'll get that y equals 2. We also have to consider where this will not exist. So that would be d prime of y does not exist. And so when we take a look at this, what we're really looking at is the denominator. So there won't be a square root. We kind of talked about the fact that this will always be non-negative, but we should make sure it's also never 0. So part of the reason I skipped this here is we're about to show it here. We want to show that y to the 4th over 4 minus 8y plus 17 won't have a problem being 0. So if we try to set it equal to 0, we will get an awful mess that we have to try to factor. So what are some things we could try to do? Well, one of the things we could try to do would be to multiply everything by 4 and see if that helps. So let's get rid of this fraction, multiply both sides by 4. We'll get y to the 4th minus 32y plus 17 times 4, which will be 68 equals 0. We then would want to see if there would be any sort of way to factor this. The real question will be if we ever end up hitting 0. So let's look at a couple of points just to kind of see that this won't happen. If y equals 0, then this mess, I'm going to just write TM for this mess, then this mess equals 68. If we plug in y equals 1, then this mess here will be 1 minus 32 plus 68, which will be 37. So until this becomes even big enough to challenge the 68, we don't have to actually worry about this getting to a point where it hits 0. What if we tried y equals 2? Well, if y equals 2, 38 times 2 will be 64. Still won't be enough to mess with this. So we'll get 2 to the 4th minus 64 plus 68, which will be 20. If only there was some way we could find the smallest this will ever get for us to kind of satisfy what we're looking at. Wait a minute. We want to find the smallest value of this? We want to minimize this mess. So if we want to minimize this mess, we want the derivative of this mess. So this mess prime would be 4y to the 3rd minus 32. And we want to minimize it. So minimizing it will be setting it equal to 0. So then we would have y to the 3rd times 4 equals 32. So y to the 3rd will equal 8. So y will equal 2. So wait a minute, the smallest it ever gets is when y is equal to 2? Well, that's what's going to happen here. But we should see what this minimum would be, or potential minimum. Right now it's just a critical point for this mess. So if we plugged in 2 to the power of 4 minus 32 times 2, I'm realizing as I'm typing this that we already did this and we got 20. So 20 is going to be the smallest this ever gets, which means it's definitely not 0. So this doesn't happen. And if it's definitely not 0, it's never going to be negative. So we don't have to worry at all, since this is the smallest it'll ever get, about this ever not existing. So this is going to be our one and only critical point. We want to make sure, though, that it's a minimum, because our goal, again, was to minimize this distance. And again, we just care about the point that minimizes it. So we want d prime and d. We're looking at this point at y equals 2. So we want to pick points around it that we could plug in pretty easily to the derivatives. 0 and, I don't know, I like 10. Why 10? 10 is an easy number to plug in. So we know the denominator is going to always be positive, right? Because we just showed it can't even be 0. So if we're trying to figure out if we're positive or negative, we're really just plugging into the numerator. So if we have 0 cubed minus 8, that'll be negative 8, which is going to be negative, and it'll be divided by some stuff that's positive. So this will be decreasing. That's a good start. If we plug in 10, 10 cubed is 1,000 minus 8 will be 992. Divided by some number that's positive will be positive. So it'll be increasing, so we do have a local min here. And so what that means for this is that this will be where we're looking at. So this is going to be our point. So if y equals 2, that tells us then that since y squared equals 2x, 4 equals 2x, so x equals 2. So the point that will minimize all of this for us is 2, 2. All right, so again, what we did is we set up our original equation, which was this distance function. We then used the constraint of what the parabola was in order to help us figure out how to get down to one variable. We then found the domain, took the derivative, checked where the derivative was equal to 0 or didn't exist, and use that to find our min, and then we're able to work towards getting the things that we wanted out of it. All right, that is 2 examples down. We'll do 2 more. All right, so now say that we have a car rental agency that rents 180 cars a day at a rate of $32 a day. For every $1 increase in rate, they forecast that 5 fewer cars will be rented. They want to know at what rate they should be renting the cars to produce the maximum amount of income. So let's kind of focus on the goal here. It's not so much a picture we can draw, but we do have a pretty obvious goal here, which is to maximize income. So income will be the number of cars rented times the rental rate. So what we've been told is that we have some control over how many times we can increase the rate. We have control over the amount we can increase the rate. So this is something to note. We can control how many times we raise the rate by $1. So X for us will be the number of $1 increases in the rate. So we know that our number of cars rented right now at the $32 price point is 180. But for every dollar we increase the price, we'll lose 5 cars. So it'll be 180 minus 5x. We also know that the rental rate right now is $32, but we could increase it by x. So that means that our objective function will be all in terms of x, and it'll be 180 minus 5x times 32 plus x. So if we go ahead and FOIL that out, we'll have 180 times 32, which will be 5,760. We'll then have 32 times negative 5x and 180 times x, and we end up getting a positive 20x, and then minus 5x squared. All right, so let's talk about our domain. Right now, we're only considering how much we can raise the price by. So we're saying that x is going to have to be greater than or equal to 0. We're telling ourselves we're not going to lower the rate. And the number of cars that we sell or rent out has to be greater than or equal to 0 as well. If we start renting a negative number of cars, that doesn't make any sense. So that means 180 minus 5x has to be greater than or equal to 0. So 180 will have to be greater than or equal to 5x. So that means 36 will be greater than or equal to x. So our domain is going to be x is in 0 to 36. So that'll be the interval we are looking at. So this is x is an element of 0 to 36, so it's got to be somewhere in there. So our optimization step will be to go ahead and take the derivative of this function, which all told is actually a pretty easy function to take the derivative of. It'll be 20 minus 10x. Now we're not going to have any domain issues here, so we just want to go ahead at that point and set it equal to 0. So if we have 20 minus 10x equals 0, then 20 equals 10x, so x equals 2. We really like that x equals 2 here in these problems, huh? So remember that we should check the endpoints and our critical points. So we want to look not only at x, but also at I of x. So we should look at 0, 2, and 36. We should look at 0 and 36 because these are our endpoints. And we should look at 2 because it is a critical point. So we plug 0 into the original function. Well, this will just be I of 0, which will be 180 times 32, which will be 5,760. We have I of 2, that will be 170. Well, might be a little easier just to go ahead and plug it into this version of the function. So that'll be 5,760 plus 20 times 2 minus 5 times 2 squared, which will give us 5,780. And if we plug in I of 36, this will be 5,760 plus 20 times 36 minus 5 times 36 squared, which will be 0. That's not good. We do not want to make $0. That would get rid of all of our profit. So this here is the highest number. So this is the max income that we can get. So we want to know what the rate should be in order for us to get the maximum amount. So notice the word rate here. We're not saying X. So the rental rate, remember, was 32 plus X, which we now know should be 2. So the rate should be increased $2 to $34. So $34 would be our optimal rate. That'll be the thing that gets us the most amount of income coming in. All right, we'll go through one more example of optimization problems. So say we have a rectangular storage container with an open top, and we want it to have a volume of 10 meters cubed. The length of its base is twice its width. The materials for the base cost $10 per square meter, and materials for the sides cost $6 per square meter. We want to find the cost of the materials for the cheapest such container. There's a lot to unpack here. First of all, we're looking at some sort of rectangular storage. So I'm going to do my best bad rectangular box impression here. And we know then that our dimensions will be length, width, and height. We also know that we're going to have an open top, which means no materials used to create the top side. Our goal is to minimize the cost. So our objective function should involve the cost, which is going to depend on surface area. Some of the things we know as constraints is that the volume equals 10 meters cubed, which is the length times the width times the height. And we know that the length has to equal twice the width. So we know that the length equals twice the width. So now we need to keep in mind what sort of sides we have and how we figure out the surface area. So if we know we're looking at the surface area, we want to look at the sides of this. So when considering the surface area, we're going to have two sides that look like length times height. So that'll be this front side and the back side. We'll have two sides that'll look like width times height. So that'll be this side and this side. And we'll only have one side that looks like length times width. And that's because we don't have a top. So what are some things that we know? Well, we know that the length is equal to twice the width. So if that's the case, we can go ahead and replace all of these L's with two W's. So this equals 2W, and this equals 2W. So that then helps us get things in terms of the width. But that also means we can rewrite this to be 2W times W times H, or 2W squared times H. Now we want to be able to use these constraints to get ourselves down to one variable. So we already know how to describe the length in terms of the width. It'd be nice if we could then take the height and also write it in terms of the width. So that means the only variable we'd have left would be the width. So taking this then, if 10 equals 2W squared H, then dividing this on both sides tells us that H will equal 5 over W squared. So 10 divided by 2 is 5, and then you get the W squared. So then using that information, this is now 5 over W squared. This is now 5 over W squared. We can then use that in order to multiply each of these by the necessary portions. So we know that the cost will equal $6 times the surface area of the sides plus 10 times the surface area of the base. So just to keep these in our heads, these are both going to be sides, these are both going to be sides, and this is going to be our base. So if we want the surface area of this, it'll be 2w times w, or 2w squared. If we want to find the surface area for this side, it will be 5 times, or divided by w squared times w, which will be 5 over w. If we want the surface area for these sides, they'll be 5 over w squared times 2w, or 10 over w. And so the surface area for the sides, because there are 2 of these and 2 of these, will be 10w plus 10 over w plus 10 over w plus 5 over w plus 5 over w. Plus 10 times 2w squared. Or at the end of the day, this will be 6 times 10 plus 10 plus 5 plus 5 is 30 over w plus 20w squared. Said end of the day like that was going to be it. 180 over w plus 20w squared is our cost function, all in terms of w. Alright, so that took a lot of effort just to get the correct cost function. We know also that when we talk about the domain here should have w be greater than or equal to 0. In fact, it should be just flat out greater than 0. And we're going to, at that point, just be looking at whatever we can make our width in order to make things work out for us. So our domain is going to be 0 to infinity. We want to minimize the cost of the box, so letting our width be as large as it needs to be is absolutely fine, because we should still be able to minimize our costs that way. So we want to then go ahead and do our optimization step. And so then we want C prime of w. And so we remember we can think of this as being the same as 180 times w to the negative 1 plus 20w squared. And so when we take the derivative here, that will be negative 180 times w to the negative 2 plus 40w, or just negative 180 over w squared plus 40w. So we'd like to figure out where this doesn't exist, which would be 0, but that's not in our domain anyway, so we're okay, or where it's equal to 0. So C prime of w equals 0, which will be negative 180 over w squared plus 40w. So that means that we would have 180 over w squared equals 40W, or 180 equals 40W cubed if we multiply the W squared over, which means we would have 180 over 40 on the left. So 4.5 would equal W cubed. Taking the cube root would give us that W should equal the cube root of 4.5. Now that's not exactly a fun number to look at, but that is then a critical point for us. So we should check to make sure that it is a min, because if it's a min, then that's something we can work with. So we want C prime and C. Here is our cube root of 4.5. We want to have something before 0, but then we can pick whatever we want over to the right. So just as a quick check, the cube root, if I can find the button for that, well, the cube root would be the same as 1/3, so 4.5 to the power of 1 over 3 will be around 1.65, which means we're really looking at 1 as a potential option for something over there, and we need something bigger than this, say, I don't know, 10. Why 10? 10's an easy number to plug in. So if we looked at C prime, if we take negative 180 divided by 1 squared plus 40 times 1, we'll get negative 140, which is negative, which means we are decreasing. Good start. We want this to be a minimum. And then if we divide negative 180 by 10 squared plus 40 times 10, we get 398.2, which is positive, which means we are increasing on this interval. Which means we do have a local min here. And our goal was to determine what the cost of the materials would be for the cheapest such container. So we get roughly $163.54 as our cost. So that would be the minimum cost we could have given these constraints in order to make a box with an open top that has a volume of 10 meters. So again, this is kind of my favorite section of everything we do in Calculus 1. The reason for that is it really starts to give you a sense of why we care about all these mins, these maxes, these different things we can find out with a function. The hardest part, usually as a student, is trying to then figure out how to figure out what the functions are, get it. But that's kind of where the magic is. That's where you get to play around a little bit and figure out what it is that you really are trying to optimize. Because you now have all the tools you need to be able to do that optimization as long as you can get down to one variable. The question then is, how do you add constraints to your problem and look at things in a way that give you that one variable problem that you can optimize. So that'll be kind of the fun thing to get to play around with.